on your video also if you want. Or it is, yeah. So I think it is not needed. I mean,
okay. I have to use then laptop, right, for video.
Okay. So
okay. Okay. So let us begin with where we work on. So for this, we need this classification theorem for surfaces. So here is the statement. So it says any compact connected oriented surface is homeomorphic to the connected sum of a two-dimensional sphere with G tori after removing B open disks with disjoint closures. Okay. So I hope everyone is familiar with the notion of connected sum here. Okay. And not only this, the homeomorphism type of such a surface is determined by this pair G and B, where G and B are non-negative integers. Okay. And so here are some examples. First is the two sphere, right? Here G is 0 and B is also 0. Second example is this torus. So here genus G is 1 and B is 0. There is no boundary component. Okay. So next we have this three-hole sphere, right? So this is also known as pair of pants. So here G is 0 and B equals to 3 and so on. So there is another example here. G equals to 2 and B equals to 2. So in this setting, this number G is called the genus and B is called the number of boundary components of the surface. So this is about the compact setting. So you can go from compact to non-compact by removing a finite number of points from the interior. So suppose you remove n points from its interior, right? So then these interior points, these are called punctures. And so now we have this notion of non-compact surface. Okay? So here let us fix our notation. So we denote a connected oriented surface of genus G with B boundary components and n punctures by this triplet GBN as subscript GBN, where G denotes the genus, B stands for number of boundary components, and N stands for number of punctures. And following Margalit, so if B equal to N equal to 0, so we denote it simply by SG.
So can every non-compact surface can be obtained from compact surface by removing the punctures?
Yes.
Can every non-compact surface can be obtained this way?
So yes, so every non-compact surface, yes, that this is all non-compact surfaces, right? So so the statement should be like, so you can determine the homeomorphism type by this triplet G, B, and N. Yes. So that will determine the homomorphism.
Right. And finite type of surfaces can be obtained by in this way.
Yes.
There are infinite type surfaces, right?
Yes. So those we are not considering. Yes, definitely. Thanks. So those are all always there. So we are not considering those. Yes. Okay. So we will be mainly concerned with this finite type surfaces, right? So with fixed G, B, and N. Yes. So you are right. Okay. Okay. So next thing here about punctures is so we will treat punctures as mark point. Okay. So instead of puncturing, we will make this mark point as distinguished points, right? So we will not remove this. We simply consider them as some distinguished points. Okay. And so here is this notion of Euler characteristic of a surface. So this we know that Euler characteristic of a surface of genus G with B boundary components and N punctures. So this is 2 minus 2g minus b plus n. Okay, and so we will see for what cases for us are more interesting. And so we will see the most interesting cases will be when Euler characteristic is negative. So it is a maybe easy exercise to list all these finite type surfaces where Euler characteristic is 0, okay, or positive. So you can see there are only finitely many cases. So where this happens, right? And in rest all the cases, right, or the generic case, we will see the Euler characteristic will be negative, right? So this you can list all, right? This is just a simple number theoretic argument why there are only finitely many surfaces with non-negative Euler characteristic. Okay. So in the sequel, we will also denote our surface by simply symbol S. Okay. So this notion we will use. Okay. And so this is a fact for which we need maybe a lot of machinery, right, to say this, that if a surface has a negative Euler characteristic, then it admits a hyperbolic metric. And towards the end of this course, we will learn about this. So we will discuss how to get this hyperbolic metric on a surface and what is the space of all metrics and discussion regarding the same. So that will be content of lecture 3 and lecture 4. So for the time being, we will just state this as a fact. Okay. So here is a quick remark, and this is a very useful remark in this area. So we will see this both topology and geometry will go hand in hand. Like so that is on the one hand, the topology controls the geometry, and in the same way we will see the geometry informs topology. Okay, and that will be seen in many of the proofs, basically topological proofs, where you will see that proof many times rely on the geometry of the space. So what kind of geometry the space admits, or so arguments are many times like you go to the universal cover and argue there. So geometry will be widely used for many proofs which looks very topological in nature, but geometry will be helpful. Okay. So the first thing we will discuss in this is curves on surfaces. Okay. So let us start with the connected oriented surface S. Okay. So what is a curve or a closed curve gamma in S? So this is just a continuous map from an interval to S, right? Such that gamma of 0 equals gamma of 1. So, or you can also regard this simply as a continuous map from a circle to your surface, right? So then you don't need to mention that this extra condition. So just regard it as a map from S1 to S. Okay. So then we will be interested in a special kind of closed curves, which are called essential. So a curve is called essential if it is not homotopic to a point, okay, a puncture or a boundary component. So in the picture, you can see some of the curves which are not essential. So in the first picture, you can see this curve gamma, right? So this is null homotopic. Yes, this is just homotopic to a point. And the second picture you can see, so it is a torus with one boundary component. So your curve is just homotopic to a boundary. So both of these are not essential, right? So if you want something essential, okay, so let me just draw something. So this is essential. Okay, so or you can draw some more curves. So this is also essential. Okay. Okay, so let us now fix our notion for fundamental group of a surface. So we will denote pi1 S. Okay, for the fundamental group. I hope you are familiar with basics of algebraic topology. Okay, so and you know, right? This group has a finite presentation. So I will not go into that, but we can definitely discuss some of these in tutorial session, right? so see, like for example, for a compact surface, like what is the presentation and how you get that. So we can discuss that. Yes. So then, so one can see there is a bijective correspondence between non-trivial conjugacy classes in the fundamental group. Okay, and if you look at just non-trivial free homotopy class of oriented closed curves. So, and how you get the correspondence? So for example, for if element of pi1, so you can simply forget the base point and get a free homotopy class. Okay. So there are other ways to see this also, like so like other way to get a correspondence. For example, you can also look in first homology. Okay. So we will see more of this. Like, okay. So here is some notion which is purely algebraic in nature. So an element alpha in pi1 is called primitive if alpha is not a power of some element. Okay, so if alpha is not equal to beta raised to power k for any beta in pi1, and where of course mod k is greater than 1. And so this you can notice, if alpha is permittive, then whole conjugacy class is permittive, right? So this is easy to see. So if because if alpha equals, right, beta of k for some beta, so then if you look at some conjugacy class, let me say gamma alpha gamma inverse, right? So this will be simply gamma beta k gamma inverse. This is gamma beta gamma inverse k. Yes. So so this is so permittivity is an invariant of whole conjugacy class. So if you look at the above correspondence, we can say the corresponding curve alpha is permittive, right, if the element in the fundamental group is permittive. Okay. So now we will come to the most important curves on surfaces. Those are known as simple closed curves. Okay. So here is the definition. So a closed curve alpha in your surface S is said to be simple if the map alpha from S1 to S is injective. That is, curve does not self-intersect. Okay. So here in the picture you can see some simple as well as complicated looking simple closed curves, right? So on this genus 2 surface, right? So this is your S2. So here you can see, right, some of the curves, right? This gamma 1, gamma 2, and this green curve. So you can see how it. So let me just start from somewhere, right? Yeah. So you go all the way, and then you just. So here you can see, right? It moves from genus, right, and go inside and come out, right, and so on. And it does it like couple of times, right? Even 3 times to be precise. So this is some simple closed curves. It does not self-intersect. And there are many complicated looking curves, in, for example, in genus surface. Okay. And I'm sure you can come up with more of this. So please try to draw enough pictures of simple closed curves. Okay. So here is a quick remark. If you look at 2 sphere S2, or let's say one sphere with 1 boundary component, 2 boundary component, or 3 boundary component, right? Or instead of boundary component, if you say same about punctures, so you will see there are no essential simple closed curves, right? And so this you might maybe spend some time see, like why on S2 there is no simple closed curve. You know, the fundamental group is trivial, yes. And what happens to, for example, let's say once punctured sphere, right? Same argument will work, right? Then you can say what happens to twice punctured sphere, why there are no essential simple closed curve. You will see every curve is homotopic to an essential curve, right? Actually essential. Right? Sorry, not essential, actually homotopic to a puncture, yes. So not essential, yes. So similarly, if you look at thrice punctured sphere or like pair of pants, so there also you will see each of the curve is like any non-trivial curve you pick, that is just homotopic to the boundary component. Yes, so this you can see, right? Okay. So next thing we study about this simple closed curves is the notion of geometric intersection number, and this is a notion associated with homotopy class of simple closed curves. So here is the definition. So let A be denote the free homotopy class of two simple closed curves in S. Right? So then one defines the geometric intersection number of A and B, yes, to be this minimum, right? So minimum of, like, take alpha in the free homotopy class of A, beta in the free homotopy class of B, yes, and look at the intersection of alpha and beta, right? Count the intersection, how many points they intersect, and take the minimum, right? So this is called the geometric intersection number, and we denote it by IAB. And in the sequel, we will abuse the notation by denoting it by sometimes I alpha beta. So to be clear here, so when I say I alpha beta, I mean intersection number of the free homotopy class of alpha with free homotopy class of beta. Okay. So this, with this understanding, we will use this notation, I alpha beta instead of IAB. So here you can see some examples. So first is a torus. So here you can see two curves, alpha and beta, and you can see that here the geometric intersection number is 1. So no matter you choose whatever curve in the free homotopy class, you cannot avoid this intersection. Yes. So similarly, you look at somewhat more maybe complicated curve alpha. So on the torus again. So you can see this curve passes through the genus, right? So let me just see. So once, twice, thrice, right? And then it comes back. Yes. Yes. So this is your alpha, and this is let's say this is beta. So then you can see that the geometric intersection number here will be exactly 3. Right? So of course this requires proof why it is 3. Right? And here is an example where you can see why this notion of geometric intersection number is like just different from just your perceiving, right? You perceive it like you get some intersection. So for example, here in this picture, genus 2 surface, you have two curves alpha and beta. So it appears to be look like there is some intersection, but apparently when you look at the free homotopy class of alpha, you can, like, it can be freely homotop to say alpha prime, and similarly beta can be freely homotop to beta prime, and they don't intersect at all, right? So the geometric intersection number of this free homotopy class of alpha and beta is actually 0 in this case. Okay. Okay. So maybe let us work on torus to understand its simple closed curves first. Okay. So how you get torus? So one way to get is, yes.
Someone is asking question, what is the importance and where can we use it?
Yes, which this geometric intersection number. Okay. Yes. Okay. So the importance of geometric intersection number is, so we will soon see. For example, if two curves have a, like, say geometric intersection number 1, for example, right? So, and suppose alpha beta are such curves, and suppose you have another set of curves, say alpha prime beta prime on a surface, right? So which the same property, say intersection number of alpha and beta is 1. So then you can always find a homeomorphism from a surface to itself, which take this one pair to other, right? So that is sometimes called change of coordinate principles. And so you can replace very complicated looking curves by some very simple curves, right, in the configuration. So this is very useful thing to have, geometric intersection number. also you will see it's when you study hyperbolic surfaces, right? So you will see its importance, right? So if you look at any two, for example, geodesics there, right? So they cannot like so there cannot be intersection, right? So they must be in, so okay, so I have to come to that. So they must be in minimal position, so that I will define soon. Okay, so some, for example, this is not in minimal position, right? This example. Okay. So geometric intersection numbers will help in topology as well as in geometry. Okay, so we will see many examples and maybe applications of this in future. Okay, I hope I answered it to some extent. Okay. So let us try to understand simple closed curves on torus. Okay. So one way to realize torus is like you look at it as a quotient of this square, right? So you have this identification, natural identification, A, B, and you get this torus. So another way to look at it is you look at R2, yes. And on R2, you look at this lattice Z2. Okay. So just look at this lattice, right? So this is like Mn. Mn belongs to integers. Yes. So you can realize torus simply as the quotient of R2 with Z2. Yes. And so we will be using this identification here. Okay. So in this setting, so if you want to look at any simple closed curve, right? So you can simply identify it with pair, right? PQ. Yes. So for example, I have drawn a simple closed curve here, right? So let's say joining 0, 0 to 1, 1. Yes. And there is a simple closed curve joining 0, 0 to 1, 0. Yes. 0, 0 to 0, 1. So let's say these are 3. So these are just lines, looks like just lines joining 0, 0, right? But you can see, so this will, if you look at in the quotient, so they will be just simple closed curves. For example, this curve 1, 1. So this will look like this, right? So it will go through this genus once, and so this will be your curve 1, 1 in this case. Okay. So this requires proof, right? So why all the like simple closed curves look like this, right? But for this, you need to look at the fundamental group of a torus, right? And see for yourself why you will get this correspondence. Okay. So this is the precise correspondence. So you either look at this PQ equal to 0 plus minus 1, right? Plus minus 1, 0, or GCD of PQ should be 1, right? Because whenever GCD is not 1, so you will get multiple curve, right? So you are going around that curve twice, or let's say thrice, right? So that is not allowed. Then it is not simple. Okay. So
the bijection is up to free homotopy, right?
which one?
The
Of
bijection.
course. Yes. Of course. So sorry, maybe I should write it. So everything, so we start with up to free homotopy, right? Yes, that's definitely true. Okay. Yes. Okay. So okay, maybe I am abusing the notation. So every time I have to write up to free homotopy. Yes. So okay. So this is a result. This proposition is from, again, this book, textbook, a primer on mapping class book. So if you look at two simple closed curves, and let's denote it by pairs PQ and P prime Q prime. So then if you want to compute the geometric intersection number, right? So this is given by this modulus of this determinant, right? Determinant of 2 cross 2 matrix PQ, P prime, Q prime. Okay. So again, when I say curves, actually I am treating them up to free homotopy. Okay. So whenever I say simple closed curves, I mean up to free homotopy. Okay. So here is a line of argument how you argue that geometric intersection number is actually given by this modulus of the determinant. So first thing one has to observe is that if you look at a curve PQ, yes, it will intersect with this 1, 0 curve in exactly Q points. So this is the first thing. So once you make this observation that that this intersection is Q, and one can check. So this Q is nothing but the determinant of like PQ with 1, 0, right? So that is, so just look at the modulus, that is Q. So we can assume that the statement holds for the case when one of the curves is 1, 0. Then how will you extend it to all pairs of simple closed curves, right? So again, the idea is you look at any map from SL to Z, right, which maps this curve PQ to 1, 0, right? So we want to argue for any pair PQ and P prime Q prime. So let us map a PQ to 1, 0 by an element of SL to Z, and this is always possible, yes, to find such an element. And this element will act on R2, right? So you know how it acts on R2. So action is simply by a matrix multiplication, yes. So if I take XY, so this is simply A of XY, yes. So action is by a matrix multiplication. So this is a linear homeomorphism, right? And it is an element of SL2Z, so it will preserve your lattice, right, Z2. So it preserves Z2. So this will induce a map at the level of quotient, right? R2 mod Z2 to R2 mod Z2, which is our torus. Yes. So let us assume that this image of P prime Q prime is P double prime Q double prime. Yes. Okay. So let us see what is the intersection number of PQ and P prime Q prime. So because this is a homeomorphism, yes. So the intersection number of geometric intersection number of PQ, P prime, Q prime, yes. So this will be same as geometric intersection number of 1, 0 and P double prime, Q double prime. So this first thing you have to be clear, right? So whenever you change two curves up to homeomorphism, yes, it does not change the geometric intersection number, right? So just you rely on our first observation, that the intersection number of 1, 0 and P double prime Q double prime. So this this satisfies the proposition, that is, it is given by this determinant, the modulus of determinant. Okay. So then you know A is in SL2Z. So you can write this matrix 1, 0 P double prime Q double prime as A inverse of 1, 0 P double prime Q double prime. Yes. So this can be done. Yes. So because determinant of A inverse is identity, so you can simply write a determinant of PQ, P prime, Q prime. Yes. So this is the line of argument that is used. Okay. If there is something which is not clear, right, or some elaboration is needed, we can discuss this in the tutorial session. Okay. This proof. But essential idea is like, so if A is an element of SL2Z, right? So determinant of, like here AB is my determinant of A, determinant of B, and but so this actually translates it to what we want, right? Determinant like this intersection of the original curves. Okay. So so next thing one should ask is like, given two free homotopy class of two simple closed curves, right? How would one determine that what is the geometric intersection number, right? There should be some way to find the geometric intersection number, right? So this next thing, the bygone criteria precisely ensures that it will give you a check that when how to find the geometric intersection number, or so a term that we should define what is the meaning of two curves to be in minimal position. Okay, so here is the definition. So let A be curves in S. Okay, so if the geometric intersection number of A and B is realized by this curves alpha and beta, right? So then we say alpha and beta are in minimal position. Okay, so for example, in the picture you can see there are two curves, right? So let me just name it alpha beta, right? So it looks like there are some intersections, right? So this is an intersection, this is another intersection, this is another intersection. Yes. So it looks like there are three intersections here, but you can freely homotope this beta to this beta prime and alpha, let's say same. And you can see actually the intersection is just one, right? So this is actually the minimal position of this. There alpha and beta are not in minimal position. In the second picture, you get the minimal position. So what was happening here? So what was the problem here? So thing was, so if you see this two regions were there, right, which were not desirable. So each of these regions, so let me just a little bit zoom in. So it looks like this, right? Or you can say like something like this. So any such region, right? So surrounded by two arcs such that like the intersection, right, region is just disk is known as a bygone, right? So bi stands for two, right? So two-gon, like. So this is just a bygone. So presence of bygones at least ensures to begin with that curves are not in minimal position, right? So whenever there are bygones, right, there is a problem. So you will have excess intersections, right? So this is the these are the questions you want to address. So first is like, how do we decide whether two curves are in minimal position? Yes. So given any two curves, so how will we decide they are already in minimal position or not? Right. Two given simple closed curves alpha and beta, how to find homotopic curves that are in minimal position, right? So you look for a free homotopic class of alpha and beta and see find curves which are in minimal position. Okay. So to ensure this, there is a actually finite criterion, so known as the bygone criterion. So what is the statement? The statement is to transfer simple closed curves in a surface are in minimal position if and only if they do not form a bygone, right? So absence of bygones means in minimal position, and presence of bygones means there are excess intersections that you can get rid of. Okay, so I will not exactly produce a proof of this, but at least you can convince yourself in one direction that why this should be true, right? So suppose we want to prove that two curves are in minimal position implies they do not form a bygone. So contrapositive is, suppose the curves alpha and beta, let's say, form a bygone, and you want to show the curves are not in minimal position, right? So if the curve form a bygone, so from a picture you can see, right? So this is some just schematic. So what you can do, you can just change these curves, right, up to homotopy and get rid of this bygones, right? So because disk is contractible, right? So you can always freely homotope, right? So let me just see. So right, so you can just freely homotope this, yes, and get rid of bygones, yes. So and similarly here you can get rid of bygones, yes. So you can simply freely homotope this, yes. So if you do this, it means you get less number of intersections, right? and so it means curves are not in minimal position. So you can homotope it to some curve so that there are less number of intersections. Yes. Okay. So this bygone criteria, so this is like a finite check, right? So if you can see two curves on a surface and you look at the intersections, you want to make sure whether they are in minimal position or not. So just see whether there are any bygones, and that is a finite check, right? Just looking at finite number of points, right? You can make sure whether they are in minimal position or not, right? And if at all there are bygones, you can just get rid of each bygone one by one, and you can answer question 2 that you will get curves which are freely homotope and to the given curves and are in minimal position. Okay. Yes. So next is a corollary of this, and it again requires knowledge of hyperbolic surfaces. So you can skip this also, like so. But this statement is really important. So if you consider two distinct simple closed geodesics in a hyperbolic surface, that will always be in minimal position. Okay. So maybe I should not discuss this, but you can just keep it as a fact. An argument is very easy. So once you are familiar with the notion of hyperbolic plane and the notion of surface as a quotient, right? So then it is not difficult to see why any two distinct simple closed geodesics in a hyperbolic surface are in minimal position. Okay. So maybe I will not go into this. Okay. So another notion that is useful in the study of mapping class groups is the notion of multi-curve, right? So what is a multi-curve? So multi-curve in a surface S is a disjoint union of simple closed curves which are pairwise non-homotopic, right? So let me just give you some multi-curves in a surface, right? So for example, so if we look at a surface, yes. So then if you look at this collection, right, this, let's say this and this, right? Let me call it gamma 1, gamma 2, gamma 3. So then this collection, right, gamma 1, gamma 2, this gamma 3. So this is a multi-curve. Okay, so let me just call test. Okay. So the point is each of these curves should be like pairwise non-homotopic. You can see alpha E, alpha J are not homotopic, right? For I different from J. So these are pairwise non-homotopic. So this is a multi-curve. On the other hand, if you look at like some picture like this, for example, if you look at this, let's say this is gamma 1, then this is not allowed, gamma 2. So this is not multi-curve, right? Okay. And also, if you look at this picture, right? Right. Let's say gamma 1, gamma 2. This is also not a multi-curve, right? Because gamma 1 and gamma 2 intersect, right? So this is. So by multi-curve means, right? So pairwise disjoint, right? And there should be no intersection. Okay. So these gamma 1 and gamma 2 intersect. So by our notion, this is not a multi-curve. Okay. 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 So next thing we will discuss is change of coordinate principle. Okay. and we will see how it will simplify things for us. Okay, so for this we will start with simple notion. Okay, so let alpha be a simple closed curve on a surface S, right? Consider a annular neighborhood of alpha, right? Let's okay, an alpha such that its closure is homeomorphic to this annulus, right? S1 close annulus, close this interval -1, 1, right? So then what can you do? You can just define this cut surface, right, of S associated with alpha, right, as this complement of n alpha, right? So you will see this S alpha has two boundary components, yes, and S alpha might be connected and it might be disconnected. Okay, so let me just give you a example of a cut surface, right? So what is cut surface? So one example is, like, suppose your alpha is this, right? So what you do? So you consider an annular neighborhood of this, right? So consider an annular neighborhood of this. Right? This is homeomorphic to, let's say, S1 cross -1, 1. Yes. So you can assume the core curve is alpha and just remove it, right? Suppose this is your S. So you can simply say remove your, like, this n, okay, n alpha from this. So you get this cut surface. Yes. Yes. So this is like S alpha. Okay. So take a surface given a curve alpha, take an annular neighborhood, right? So this is why n alpha. Okay. And just remove this annular neighborhood of the curve. So you get a surface which is known as the cut surface. Okay. So there are two possibilities. So one of the possibilities, this cut surface is disconnected, and another possibility is this cut surface is connected. So based upon that, we have this definition. So a simple closed curve alpha in S is called separating if the cut surface S alpha is disconnected, right? And if it is connected, then you call it non-separating, right? So what will be the example of a non-separating curve? So
sorry to interrupt. We are cutting the open annulus, right? That is in
open
cut surface, the
annulus,
boundary.
open annulus. Yes. So that's why I'm using closure. Sorry. So take an annular neighborhood. Okay. So by neighborhood I mean the open neighborhood. Okay. So such that the closure is this. Okay. So when I am cutting the open annulus, so that you will get two boundary components. Okay. So maybe you can call one of them as alpha 1, alpha 2. Okay. So on the other hand, you have you could have a situation where, let me just take torus. So suppose your curve is like this. Let's call this alpha. So you can take an annulus like this neighborhood. Yes. So of course you have to take. So let me just call it an alpha. So then what you will get? Yes. So you will get something like this. This. So actually, it is an annulus here. Okay. So let me just call it alpha 1, alpha 2. So resulting surface is actually connected, right? So here it is disconnected. Yes. So this is your S alpha. Yes. So first case, when the resulting surface is disconnected, you call your curve to be separating. In the other case, it is not separating, right? Non-separating. Yes. So maybe you can next ask questions, how many non-separating curves are there up to free homotopy, or maybe some more equivalence is required, and how many, let's say, non-separating curves, right? So there are infinitely many, of course. But if you look at maybe mode it out by some equivalence, you will get only finitely many. So let's see what that is. Okay. Yes, so here is a picture of separating and non-separating curve. Okay. So here you can see maybe more than one non-separating curve. This all are non-separating in the second picture. Okay. Okay. Yes. So this is a theorem which states that if you know the cut surface, right? Right. So it's of curve alpha, right? And suppose those are same, then there is an orientation preserving homeomorphism which takes a curve alpha to beta, right? So only thing you need to make sure is the cut surfaces are homeomorphic. So in some textbook, even the definition of cut surface, there is some additional information is also there sometimes. So when you remove this annulus, right? So they keep track of where was the gluing, right? So that convention is there. So for example, here, so I would say that so you might encounter that. So you can recover your S from this, right? So let us call it S alpha. Yes. So then there is an identification. So by which you will, let's say, you can just reverse this process. So you can just take the annulus, right, and just glue it by some map, right? So, and gluing has to be exactly it is just a reverse of this, right? So first you remove an annulus, right, and then you can glue it back to recover your S. Yes, and of course gluing it by some homeomorphism H, right? So such that this alpha 1 is mapped to this this one boundary component of this annulus, right, and alpha 2 is to other. Yes, so in that way you recover S. So many times the notion of cut surface, this information is also there, right? So in some textbook it is followed, right? So when they say cut surface, so they have this information also where the gluing happens. Okay, and they have record of this by some map. Okay. Okay. So let's see how to look at this. So one case is if alpha is non-separating, right? So then you can see by classification of surfaces. So what is your S alpha, right? So suppose your S has some genus G, then S alpha will be homeomorphic to surface of genus G minus 1 with 2 boundary components, right? Because whenever you cut it along a non-separating curve, right, you will get 2 boundary components and surface is connected and genus will be 1 less. Yes. And on the other hand, if alpha is separating, yes. So what you will get? So you will get S alpha is homeomorphic to disconnected surface like this, right? So let's say SK1, so where 1 stands for one boundary component, and SG minus K1. Yes. And for some K, of course, less than G. Okay. And of course, when I say this separating curve, you also have this null homotopic, right? So that don't consider that. Okay. Otherwise, it's trivial. So that's why I have written K less than equal to G. Otherwise, you have to write K equal to G here. Yes. So then you have to just go back to this, you just have to recover your S from this. Okay. So just reverse the process in each case, and you will get homeomorphism by classification of surfaces simply. Okay. So this is one way of looking. So if you just consider a non-separating curve, so what is the upshot? Then up to homeomorphism, there is just one non-separating curve, isn't? Because you know, right? So there is only one surface, right? Homeomorphic to SG minus 1, 2. Yes. So if you know the cut surface, right? If you know it is like your curve is non-separating, yes. So then there is just one choice, yes. So let me just say that. So what is a consequence? Consequence is like if let's say alpha is a non-separating curve in S, right? Of course, up to when I say curve, I mean up to homotopy, right? So if you take a non-separating curve and we define, let's say beta is equivalent to alpha, if and only if, right, there is a homeomorphism, let's say f S2S such that f of alpha equal to beta, right? So then, so if you look at set of all non-separating curves up to this equivalence, right? So how many are these? Just one. So cardinality of this set is just one. So there is only one non-separating curve up to, right, homeomorphism. Yes. And on the other hand, if let's say alpha is separating, let's say for simplicity in SG, right? And say G is greater than or equal to 1, right? So then you know what happens, right? When it is separating, so what it will give? So it will correspond to, right, the cut surface which is homeomorphic to, yes. So you have something, let's say SK1 disjoint union SG minus K1, yes. So once you know this number K, you know the cut surface and you know your separating curve up to homeomorphism, right? So similarly, you can define an equivalence here. So now the question is how many equivalence classes are here, right? So that is like if you want to count, let me say separating curves up to the same equivalence. So what is this number? Anyone? Yes. Right. So all you have half the
G.
Half the G. Yes, good guess. So you have to take the floor, right? So for example, if G is 1, yes, there is no, right? So let me say just take, let's say G equal to 2. Yes. So how many are there? So you just say 1, right? Half the G. Good. So let me just take genus 4 to be. So how many? So we just have to look at this configuration, like this K1 and G minus K1. How many ways you can partition it, right? So if G is 4, right? So just have to look at 1 plus 3, 2 plus 2, right? There is just 2 ways. So for example, this curve and this curve, right? So they are in both equivalence class, yes. And then there is this, right? Yes. So this is just G by 2, yes. Okay. Let us now come back to some other result in this direction. So this is just one case, like when you have just one curve, right? This is your change of coordinate principle. So what about if you have more than one curve? Let's say you have a pair of curves, right? One pair is alpha 1, beta 1, other is alpha 2, beta 2. Yes. So both are simple closed curves, right? Like both pair contain simple closed curves such that the geometric intersection number of alpha 1, beta 1 is 1, and so is alpha 2, beta 2. Okay. So then, so once you have this data, then there is a homeomorphism phi from S to S, which takes alpha 1 to alpha 2 and beta 1 to beta 2. Okay. So let's see how we argue this. So what we will do? So first we look at the cut surface, right, as alpha 1. Okay. So just consider the cut surface as alpha 1. So here, so what will be beta 1? Beta 1 will correspond to an arc with endpoints on the boundary curves, right? So maybe I need a picture, right, for this. So yes, so you have something like, so let me just take alpha 1, let's say this is beta 1. Okay, and suppose this is alpha 2, beta 2, right? So both have the same geometric intersection number 1. Okay. So then you want to look for a homeomorphism which maps alpha 1 to alpha 2, beta 1 to beta 2. Yes. Okay. So first thing is you look at this cut surface as alpha 1. Let's analyze this pair alpha 1, beta 1, right? So what you get, so what is as alpha 1, right? So you just look at this cut surface as alpha 1. Yes. So on the surface, so what do you do, right? So let's see what beta 1 correspond to, right? So your curve beta 1 will correspond to an arc, isn't it? So if you look at beta 1 is nothing but this, just an arc on the surface, right? Once you remove this, so this is just this arc. Yes. So your beta 1 will correspond to an arc here. Yes. So this is the first thing, observation. Okay. Okay. So with endpoints on the boundary curves alpha 1 and alpha 2, right? So of course in cut surface as alpha you have two boundary curves, right? Alpha 1 and alpha 2. Yes. So let us write this as maps from S1 to boundary of S alpha. Okay. So then you just cut it, right? So cut it along the arc beta 1. So this gives you the cut surface. Let's call it S alpha 1, beta 1. Okay. So you have this cut surface alpha 1, just cut along this arc beta 1. So then you have a record, right? Where are these endpoints, right? So when you cut along this, so this, what you will get? You will get one more boundary component. So let's call it delta 1, right? And you have 4 marked points. Yes. Corresponding to this. Yes. So just make them distinguished. So just call them marked points. So it means you recognize those points, right? You have the information. So similarly, you do the same process for S alpha to beta 2. Yes. Consider the cut surface as alpha 2. Take the arc, right, corresponding to beta 2, and you will see it will correspond to 4 marked point, right? And one boundary component, let's call it delta 2. Yes. So then, so this boundary component delta 1 and delta 2, the configuration wise both are same, right? So you have the information, right, about 4 marked points, right? And these are made of out of arcs, right? So you can find a homeomorphism, right, which takes this delta 1 to delta 2 and it maps marked points to marked points, right? So this you can always make sure. Just one boundary, right? It is a circle, right? So circle you can always map to circle, and you make sure that marked points are mapped to marked point. So then, so you have the information about the gluing, right? How you can get back your surface from the cut surface as alpha 1, beta 1. So just use that information and extend this map P to just map from cut surface as alpha 1, beta 1 to as alpha 2, beta 2, and making sure these gluing relations are satisfied, and it takes your, okay, so I should not write gamma 1. There is no gamma 1, right? Taking just delta 1 to delta, right? So that is the sketch. So main thing is, so once you have one boundary component delta 1 with this 4 marked point,
So there is a question,
Two
what
other.
are the mark points? There is
Yes.
a question, what are the mark
Okay.
points?
Okay. So for this you have to cut. Okay, let me cut it. Okay. So for example, in the picture here, you can see these 2 points, right? I'm
We
not sure.
can't
So
see.
let me just zoom in a little bit.
It's stuck, I guess.
Is it visible?
No.
Huh?
Your picture is, I mean, we can see your note, but
Yes.
are you drawing anything?
Huh?
No, we can't see it. Maybe you just
I don't-
scroll down.
Now?
No,
Now?
no, we can't see your screen. I mean, what you are doing now.
Okay. So what are you able to see now? Like
So this page number 19 is there.
19. I am not on page number 19.
Okay. Maybe you stop sharing and then share the screen.
Okay. So what should I do?
Stop share. Stop sharing. Okay. Yeah. Maybe you can rejoin the thing. So maybe you can stop sharing and again you can start the sharing.
So there is a problem.
Yes. Now we can see.
Now it is visible.
Yes.
Good. So
Yes.
so first thing is, like, you take this annular neighborhood of alpha. Yes. This is alpha. And there is your curve beta. Okay, let me just.
Are you writing anything?
I am writing.
Oh, we can see on the S alpha 1. This. We can see S alpha 1 and below there is a closed curve kind of thing. And above there is a genus 2 surface. This alpha 1, beta 1, 2 curves. And
So you cannot see the new picture I have drawn. Like, I have a little bit zoom in. There are 2 pictures.
Just draw something.
Okay, so maybe I will erase it and again draw.
Okay.
Let's see.
I think something is not working.
Now,
No.
is it visible?
No. Yes.
Yes.
Please again stop the sharing and I think again to try to do the same thing. Let's see.
Don't know why.
So is there a power cut from your side?
Where?
Can hear some sound.
Now?
No. So you have to share the screen.
Wait, I shared. Don't know.
is taking time.
Hmm?
It is taking time. Yeah, please draw something.
Okay, so let me erase. Now,
No.
is it visible?
So the screen is visible, but did you erase something? That part is not visible.
First picture.
First picture.
I can erase like whole page. Let's see if you can.
Now it is, yeah. Erase the whole page and
I have erased the whole page.
okay.
It is still showing something.
So some part is erased. Yeah, so now it is gone. Yeah,
So it means there is
the
a
net is
clear
very
lag.
slow. Yeah,
Ah.
net is very slow, I guess, from your end.
Yes.
And so another thing you can do,
Mhm.
so you just check this view options.
Hmm.
And oh no, this part is not there. Okay. Okay, yeah, please do it once again. Share
So
the
I will
screen.
stop sharing. Okay.
Now again do start the sharing.
It is again showing I have stopped.
Yeah, it is coming.
Huh?
Yes, please now. I think now it is working. So please write something.
Let me.
Yeah, now I think it is working. Yes.
So
yes.
can you see?
Yeah, now it is working.
Okay. So yes. Yes. So you can first take a, let's say, neighborhood of alpha 1. Yes. So here you can see there are 2 points, right? When you remove this, right? This.
Yes.
But once you cut along this beta 1, right? So this point, right? So this, so you will get like, so you have to identify it with some other point, right? So each point will correspond to 2 marked points. So that is the point. So when you cut along alpha 1, beta 1, so each point will correspond to like 2 points. Yes. So that was enough.
First, you are taking out this tubular neighborhood of this alpha 1.
Yes. Tubular neighborhood of this alpha 1.
Alpha 1. Okay.
Annual, just some annulus, right?
Okay.
So because first you define this cut surface as alpha 1. Yes. So then your beta 1 will be this, right? But if you cut along this beta 1 as well, right? So then this point, yes, this each point will correspond to 2 points. So that is the meaning of 4 marked points. Yes.
So marked points lie at the boundary.
Yes.
Okay.
Exactly. Yes.
Okay. Yes.
Otherwise, we cannot keep track of like how will you get? So when you take this homeomorphism going from a boundary to the other boundary, right?
Right.
So you have to make sure like how each arc is mapped. Yes. So this will union of arcs, right? Bound.
Correct, correct.
Okay. So I hope the idea is at least clear, but we can make this precise. Okay. So where
So another question I want to ask. Suppose I change the intersection number. So here the intersection number is 1.
yes.
And I restrict this to non-separating curves, and intersection number is k. Still you have the same kind of result?
I'm not sure. Like for example, here is another situation where at least answer is positive, right? I can say that maybe where it is positive, like similarly. No, not in every situation answer is positive, that I know. For example, in this situation, so let me just say one more situation. Okay. So suppose I have, let's say, so something like this, right? So then it is positive, right? So these are called bounding pairs of maps. So for example, if I have the alpha 1, beta 1 like this, right? And suppose you have some other, and of course there is something more to it. Like there is like this genus, right? Suppose there is like, so let me just say, for example, this is of the type, let me say 1, 2, right? Bounding pair. You got it? So on the left you have one genus and here you have two genus. So if you know this, you have this information, then again change of coordinate principle works in this setting. So for example, okay, let me just check. So here it is 2. So this one. Alpha 2, beta 2. Yes. For alpha 2, beta 2 also the same data is same. Yes. So if you look at the after cutting along alpha 2, beta 2, you will also get two disconnected surfaces. One is genus 2, other is genus 1. Yes. So you have the same like.
No. What I'm saying is that take alpha 1 and beta 1, and all the curves are non-separating.
Yes, alpha 1 and okay. So let me just okay.
All the alpha i's and beta i's are
non-separating.
And intersection number of alpha 1, beta 1 is same as the intersection number of alpha 2.
Okay. So I'm not sure about that. I'm not sure. I don't know the answer. Okay, for this. Yes.
So there is some question.
Okay. So I don't know the answer to this. Okay. So if so, the question is like, what happens if you have two non-separating curves, and if you change the intersection number from 1 to, let's say, any other number? Yes.
Correct. Yes.
Yes. So okay, right now I don't have the answer. I'm not sure because all I know is it won't work always. So only some special cases it works. Right.
Okay.
Right. So I'm not sure whether this for number different from 1 it works.
Okay.
Okay.
So someone want to ask some question.
Yes.
Please go ahead.
Okay. Right. So now
someone raised hand. Please go ahead.
Should I like pause?
Sorry, I raised.
But
I think I was not able to understand what the question was, so I raised the hand. But now it's okay.
Okay. All right. Okay. Yeah. So Shiv, you can proceed.
Yes. Okay. So now we are inching towards defining metric class group. Okay. So for this, we need the notion of isotopy. Yes. So two simple closed curves, alpha and beta, in a surface S are said to be isotopic. Okay. First thing, if there is a homotopy, H from S1 cross, let's say, interval 0, 1 to S, such that for each T, right, this curve S1 to S is actually simple, right? So then you say it is an isotopy. Right? Homotopy, I hope everyone knows, right? So this is H is continuous, right? H at time 0 it is alpha, at time 1, right, it is beta. Yes, that is homotopy. And what is isotopy? It says So for each t, you have this curve, right? S1 to S fixed t, x goes to h of xt. Yes. So this curve should be simple. So then you say your homotopy is an isotopy. Okay. Okay. So these are some results from differential topology, which I will not prove, but I will just state. So first is this fact one. It was first proved by Bayer. So let alpha and beta be two essential simple closed curves in a surface S, right? Then alpha is homotopic to beta if and only if alpha is isotopic to beta. So whenever needed, we can move between homotopy and isotopy, right, in surfaces. So that is upshot. Okay. So next is another definition. Of course, that is the most important definition to define mapping class group. So what do you mean by isotopy of a surface? Okay. So an isotopy of a surface is a homotopy, first of all, right? So that is like, so it is a map from S cross I to S, where I mean the unit interval 0, 1, such that for each t, this map, you look at this map, F subscript t from S to S, X to H of xt. So if this is a homeomorphism, okay, so that this is by isotopy, you mean homotopy by a homeomorphism, right? So in general homotopy, like there is no guarantee that each of this map is a homeomorphism. This could be like any continuous map, but here you demand that each of this map, right, ft is a homeomorphism. Okay, so then you call it is a isotopy. Okay, so this is again another fact. This is a result in differential topology, and its proof goes back to Munkers. So again, let S be a compact surface. Then every homeomorphism of S is isotopic to a diffeomorphism. So this is a rather very strong result, right? So you can change the category completely, right, from here. Right? So if once you are working in with homeomorphism, instead you can work with a diffeomorphism, whatever is convenient to you. It depends. So depending upon the convenience, you will change between homeomorphism or diffeomorphism. Okay. So we are in a position to define what is mapping class group of a surface. Okay. So again, the notation is same. S is a surface, right? Connected, orientable, genus G, B boundary components, N punctures, right? And this homeo plus S boundary S. So what it means, it is the group of orientation preserving homeomorphism, let's say H on S, which when you restrict to boundary, it is actually point-wise identity. Yes. So let us look at this set. So this is a group. So then what is mapping class group? So mapping class group is on this group of homeomorphisms, you define an equivalency relation up to two maps are equivalent if they are isotopic, right? So this quotient, right, is called the mapping class group, right? The homeomorphisms up to isotopy. Okay. Where, of course, when we say isotopy should fix the boundary pointwise. So there are some variations with this definition in literature, right? So sometimes, like some people like define mapping class group as, so they allow the boundary to remain invariant, right? Not just fixing pointwise. So there are some variations of this. So, but we will follow this following Margaret. Okay.
So in definition, puncture has no role, right?
So punctures are?
In definition, you didn't mention any conditional punctures, right?
Yes, I will mention this. This is the next remark. Okay, thank you. So and we fix our notation as mode of S for the mapping class. And so here is this remark about punctures. So if let's say S has punctures, okay, So then what is mode S? So all these conditions with, so you allow the punctures to be permuted. Okay, so the set of punctures should remain invariant. That's it. So punctures need not be like remains point-wise fixed, right? So your punctures are nothing but marked point or distinguished point. So you allow them to be permuted here. Okay, so that is the difference between boundary and puncture. So we have to be careful what we are dealing with. In boundary, you say boundary is point-wise fixed, but punctures, a permutation is allowed. Okay.
Yeah, Shiv.
Hmm.
The time is up. Maybe I think it is a good point to stop here.
Okay, time is up.
Yeah, this four.
Okay. Yes.
So maybe you can continue this with then the next class.
Okay, so so when should I like?
Tomorrow again, right? You can continue.
Okay. No, that I can.
And,
tutorial like.
so tutorial, it will start from 4 o'clock. Is it okay, or you want to start it?
4 is fine with me. Okay, it is 3:45. Okay, already. So can we make it maybe 4:10?
Yeah,
Or
sure.
it will be late. So that will be better.
Okay, yeah.
Okay.
Okay.
Thank you everyone for the attention.